Hello students, today we are going to discuss a very important topic of chemical kinetics, that is first order reaction. So how first order reaction proceeds, let's discuss. In first order reaction, let's suppose a reactant A forming the product B. At time t is equal to 0, let the concentration of reactant is A and product 0. At time t is equal to T, the concentration of reactant is A minus X and concentration of product is X. Now we know that the rate of reaction is proportional to the concentration of reactant. So we have introducing here a constant, that is rate constant for the reaction K. This implies minus dA by A is equal to K dt. This implies dA by A is equal to minus K dt. In this way, dA by A is equal to minus K dt. On integrating this, we get from limit A naught to A, we get where A naught is the initial concentration and A is the concentration at time t of reactant. So ln A from a limit A naught to A is equal to minus K t. Here limit 0 to t, so this will be equal to limit 0 to t. This implies ln A minus ln A naught is equal to minus of K t minus 0. So ln A minus ln A naught is equal to minus of Kt. This implies ln A naught minus ln A is equal to minus of Kt is equal to plus of Kt. Multiplying both sides by negative, so this negative positive and this negative suppose change the side of this here and this. Okay, this implies ln A naught by A is equal to Kt. Here we have natural log, convert it into the log with base 10. So log A naught by A is equal to Kt. This implies T is equal to log A naught by A, and here multiply by 2.303 to convert this natural log into base 10 log divided by K, where K is the rate constant. So in this way, this is the integrated rate law equation for first order reaction. Log A naught by A. Now calculating T half-life. So T half-life, A is equal to A naught by 2 and T is equal to T half-life. Implies T half-life is equal to 2.303 by K log A naught upon A naught by 2. So T half-life is equal to 2.303 log A naught by A naught, and this 2 comes here into 2, this cancels, is equal to 2.303 log 2 by K here. So T half-life, this implies T half-life is equal to 0.693 by K. This is the half-life for first order reaction, 0.693 by K. Now let's calculate the lifetime for first order reaction, total lifetime for first order reaction. We have discussed the lifetime for zero order reaction. It is twice of half-life. So here we have, let product A to be A naught at t is equal to 0 and 0 at t is equal to 0 and t at t is equal to t A naught minus x and x. In this way we have derived this equation, t is equal to 2.303 by k log A naught by A. Now total lifetime means tau is equal to 2.303 by k log A naught is a constant, so it remains as it is, but this means we have this A. Let's suppose this is equal to A, so reactant remains 0, reactant becomes 0 at t is equal to tau. At t is equal to tau, reactant finished, all the reactant converted into product. So in this way we have reactant concentration here, A is equal to 0, so this is equal to log 1 by 0 means log infinity, and it is equal to infinity. So lifetime for zero order reaction, first order reaction is infinity. In this way, let's suppose a reactant concentration at time t is equal to 0 is equal to A naught. When it halves, it takes half-life, again it halves, again it takes half-life, again it halves, it takes half-life, and in this way this process continues till infinity. So the concentration at after nth half-life is calculated by formula A naught. A is equal to A. This concentration is concentration after nth half-life passed. So A is equal to A naught by 2. Here A naught is the initial concentration of reactant and A is the concentration of reactant after nth half-life passed. And here N is the order of reaction. No, sorry. N is not the order of reaction here. Here we have, here N is the number of half-life passed. Let's suppose here we have a reaction with A naught equal to 2 mole per liter. Now, and reaction is first order. Now let's tell me, after passing 5 half-life lifetime passed, what is the concentration of reactant? So concentration of reactant is equal to A naught means 2 upon 2 to the power 5 is equal to 1 by 2 to the power 4 is equal to 1 by 2 into 2 into 2 into 2 is equal to 2 to the 4 to the 8 to the 16, 1 by 16 mole per liter. In this way we will calculate the concentration of reactant after nth half-life passed. Now, as we know that for first order reaction, after calculating from the above formula, we have T 75% by T 50% is equal to 2. This relation is important for solving question in examination. Now let's deal with the graphical aspect of first order reaction. So first graph we have, let's change the color. So reactant versus time graph. Reactant versus time graph. So we see that we have relation ln A naught by A is equal to Kt. This implies, on reversing this, ln A by A naught is equal to minus of Kt. This implies A by A naught A by A naught is equal to e to the power minus Kt. E to the power minus Kt. This implies A is equal to A naught e to the power minus of Kt. So this is the relation. This is the relation between the concentration of reactant at time t and the time. So this relation A is equal to A naught e to the power minus Kt. This is the relation. Following this relation we have the graph. Here the concentration of reactant and here time. So graph is like this, and it is not touching this axis, time axis, and here it is A naught. It is following the equation A is equal to A naught e to the power minus Kt. So this is the concentration of reactant and time. So this is the graph between the concentration of reactant and time. Now rate versus time graph. So we know that rate for first order reaction is equal to rate constant into concentration of reactant. So as we know that concentration of reactant A is equal to A naught e to the power minus Kt. This implies rate is equal to K. Here putting this value A naught e to the power minus Kt, A naught e to the power minus Kt. Here we have rate is equal to K A naught e to the power minus Kt. So again this equation is like the previous equation. So here graph is also like this, and this graph doesn't touch this time axis. Here time and here rate, and this follows the equation rate is equal to K A naught e to the power minus Kt, and here it is K A naught. Now we have again rate versus reactant graph. So how this graph varies, let's see. So we see for first order reaction rate is equal to K. Here is the concentration of reactant. So this is of type y is equal to mx. So this graph is like this. Here rate and here reactant, and it follows the equation rate is equal to K into concentration of reactant. Now we have fourth graph, product versus time graph. So as we know that A is equal to A naught e to the power minus Kt, and from the above slides we see that, let's see it here, the concentration of product at time t is equal to A naught minus x. So putting A naught minus x here, so A naught minus x is equal to A naught e to the power minus Kt. This implies K is equal to A naught 1 minus e to the power minus Kt. So we have this equation, sorry, this is not K, this is X. Here X is the concentration of product. So this is the concentration of product and this is time. So this have graph like this. Here we have, so this is A naught and this is concentration of product, and here T tending to infinity, because the concentration of product, here time axis, here the time tending to infinity, and when time tends to infinity, then at infinity they touch each other, means they never touch each other. In this way we see that for the product concentration to be equal to the maximum concentration of reactant, the time taken will be the infinite time. So for completion of a first order reaction, we see that time taken will be infinity. So this graph is like this, and it never touches the maximum concentration of, that is A naught. In this way we have discussed all about the first order reaction. Thank you very much, and please rate, please like, share, subscribe and comment. Thank you very much.